When you look at those incredibly tough exams, like the IIT JEE, you have to wonder, what really separates the top 1% from, well, everyone else? And let me tell you, it's not some kind of photographic memory. Nope, it's something way deeper. It's about a real, true mastery of the core principles. So, what is that secret, right? What's the key that unlocks those problems that are literally designed to stump even the smartest people in the room? And here it is. The answer is, it's not about what you know, it's about how deep you know it. It has nothing to do with how many facts you can cram into your brain. It's all about the depth of your understanding. See, when you master the foundations, you get this power to solve problems you've never, ever seen before. Okay, so to really see this in action, we've got to go right back to the beginning, the ground floor of science. We're going to ask the most basic question there is. What is all this stuff around us actually made of? Well, the official scientific term, of course, is matter. Simple, right? Your phone, the air you're breathing right now, even you, it's all matter. And that's a pretty simple definition for a concept that is, well, the foundation of literally everything. But that just kind of kicks the can down the road, doesn't it? Okay, so everything is matter, but then what is matter itself made of? What are the ultimate building blocks? For literally thousands of years, that question was left to philosophers. It was all theory and debate. But then, this quiet English school teacher, a guy named John Dalton, comes along and just sparks a complete scientific revolution with one simple but incredibly powerful idea. So before Dalton, the best idea science had was this ancient concept of 4 elements, right? Earth, air, fire, water. It sounds kind of cool and poetic, but it's not very useful for, doing actual science. Dalton's idea was a total game changer. He said, no, forget all that. All matter is made of these tiny, fundamental particles, and he called them atoms. This was a huge shift from some kind of mystical blend to actual discrete building blocks. And this quote from him, wow, it just perfectly captures how strongly he believed this. For Dalton, these atoms were permanent. They were indestructible. You couldn't just create them or destroy them. All you could do was rearrange them. And believe me, at the time, this was a totally radical way to think about the world. But see, Dalton didn't just stop there. He didn't just say, hey, atoms exist, and drop the mic. No, he laid out a set of really simple but profound rules about how they behave. And these rules, they became the absolute bedrock of all of modern chemistry. Okay, so these are the 4 pillars. Let's break them down. First, pretty straightforward, all matter is made of atoms. Got it? Second, atoms of the same element are identical, but they're different from atoms of other elements. So, every gold atom is the same as every other gold atom, but they're totally different from, say, an oxygen atom. Third, atoms combine in these simple whole number ratios to form compounds. Just think of H2O. It's a clean 2-to-1 ratio. And finally, number 4, chemical reactions are just a rearrangement of these atoms. Nothing gets created, nothing gets destroyed, it just gets reconfigured. Honestly, the best way to think about this, and it's a perfect analogy, is Lego bricks, right? You've got different kinds of bricks, red ones, blue ones, yellow ones. You can't just snap a brick in half. All you can do is click them together in simple combinations to build something totally new. That's it. Atoms are basically the universe's Legos. And this brings us right back to that second rule we talked about. A carbon atom isn't just different from a hydrogen atom in some vague philosophical way. No, it's measurably different. It has its own specific, distinct mass. And this property, the fact that you could test it and measure it, is exactly what took Dalton's idea from just a cool philosophy to actual real science. Okay, so you might be thinking, cool history lesson, but what does this have to do with me acing my exams? Well, here's the thing. Getting a handle on these 200-year-old rules isn't just for a history test. It is the absolute key to unlocking the toughest problems on an exam, like the IIT JEE. So why is this like a superpower on an exam? Well, because if you really get it deep down, you just instinctively understand why mass is conserved in a reaction. It's because no atoms are lost. You master stoichiometry because you know atoms have to combine in these fixed ratios. It means you can actually reason your way through a tough problem from the ground up, instead of just frantically trying to remember some formula you memorized. And that is the whole point. An exam like the IIT JEE is literally engineered to test this exact kind of foundational thinking. It's built to separate the people who just memorize stuff from the people who genuinely understand it. When you master Dalton's simple rules, you're not just learning chemistry, you're learning how to think like a scientist. And that's the game. Now, of course, science didn't just stop with Dalton. I mean, he gave us the ground floor, but man, there were so many more floors to build. He called his atoms indivisible. But about a century later, scientists found out that wasn't quite the whole story. So what happens when you finally get the power to split the unsplittable? Well, that is a story for another time.
The IIT JEE, let's be real, it feels like a mountain, doesn't it? Just this massive, impossible challenge. But you know what? Every single mountain has a starting point, a first step that makes the whole climb possible. Today, we're going to pinpoint that exact spot for chemistry. Let's get into it.
So let me ask you something. When you're staring down a problem that just seems ridiculously complex, where do you even begin? What's that one universal first step?
You don't try to beat the final boss on day one, right? No way. You learn the controls. You figure out the basic principles. You master the rules of the game. And that is exactly our game plan for IIT JEE chemistry.
Now, let's reframe this whole thing. Chemistry isn't just one of 3 subjects you have to get through. For the IIT JEE, you have to think of it as the central science. It's a huge piece of your blueprint for success, connecting physics and biology, and honestly, it's often the highest scoring section if you get this foundation right.
And listen, if you're building something massive, something important, like your future rank in the IIT JEE, you have to start with the foundation. So everything we're about to cover, this is that ground floor. We are laying the concrete for your chemistry blueprint.
So what is this foundation? Well, think of it like learning an alphabet. Before you can write an award-winning essay, you've got to know your A, B, and C's. In chemistry, that alphabet is the absolute building blocks of matter itself. So let's start with the letter A in our chemistry alphabet, the atom. This is it, the fundamental particle, the ultimate Lego brick. Imagine the smallest possible piece of gold you can have that is still gold. Yep, that's a gold atom. Everything is built from these things.
Okay, so what happens when these Lego bricks start clicking together? Well, you get a molecule. It's really just a team of atoms bonded together. The oxygen we're all breathing right now, it's not one oxygen atom floating around. It's a molecule of 2 of them stuck together, O2. 2 bricks, click together, that's it. So, what if you have a huge pile of just one type of atom, like a giant bucket full of identical Lego bricks, all the same shape, all the same color? That, my friends, is an element. A bar of pure iron is an element because it's made of nothing but iron atoms. The key word here is pure.
But what if you take different kinds of Lego bricks, say some blue ones and some red ones, and click them together in a very specific pattern? Now you've got yourself a compound. Water, H2O, is the perfect example. It's a compound made from 2 totally different elements, hydrogen and oxygen, bonded together.
And this slide just lays it out perfectly, doesn't it? You see the element on the left, pure, all the same particle. Then the compound on the right, a specific structure made from different particles. I'm telling you, this distinction, pure versus combined, is at the absolute heart of so many IIT JEE questions. Okay, so we have our alphabet, atoms, molecules, elements, compounds. Got it. But how do they, play together? They don't just do whatever they want. They follow these super strict, unbreakable rules. And these are the laws of the game. And here they are, your cheat codes. Seriously, the laws of chemical combination. Number 1, mass is conserved. Whatever stuff you start with, you have to end with the same amount of stuff. Easy enough. Number 2, proportions are definite. This one is huge. It means water is always H2O. It always has the same ratio of hydrogen to oxygen. Always. And 3, ratios are simple. Elements combine in nice, clean, whole numbers. Now, how does this score you points? Okay, think of a classic problem, like 10 grams of a metallic oxide on reduction gives 8 grams of pure metal. That sounds kind of tough, right? But the key, the entire key, is the law of definite proportions. You know the exact mass of metal and the exact mass of oxygen that combined. That one simple rule just unlocks the whole problem. It's beautiful.
So we've covered the blocks and we've covered the rules. Now you might be thinking, this is kind of basic stuff. Why are we spending so much time here? Because this is the secret weapon. This is how you go from these simple ideas to solving really complex problems. This right here is probably the most important thing you'll hear today. That terrifying stoichiometry problem, that really intricate question on chemical bonding, deep down at its core, it's just a clever combination of atoms, elements, compounds, and the laws they have to follow.
Remember that metallic oxide problem? It wasn't about some obscure formula. It was just about applying one simple rule. They're not inventing new Lego bricks for the exam. They're just stacking the same ones you already know, but higher.
So knowing that it's all just simple blocks stacked in clever ways, let me ask you this. With limited time and energy before the exam, what's the smartest, most strategic place for you to focus your effort to get the biggest return?
Exactly, on the foundation. You don't get better at building skyscrapers by staring at the sky. You get better by becoming an absolute master of concrete, steel, and the laws of physics. It is exactly the same here. Master this foundation.
So let's end with this thought, right? Master the alphabet and you can write any story you want. Master the rules of a game and you can win. It's the same thing in chemistry. Master these basics and you can solve any problem they decide to throw at you.
So there you have it. The code is cracked. That first step is crystal clear now. You have the blocks. You have the rules. The only question left is, what are you going to build with them?
Hey there, and welcome to The Explainer. Today, we're going to put on our detective hats, maybe grab a lab coat, and solve a classic chemical mystery. So, imagine this. You get handed a vial of some random white powder. How in the world do you figure out what it actually is? This is the fundamental challenge for any chemist, right? We're going to walk through the clues, step by step, and crack this thing's molecular identity. Okay, so our first step in any investigation, you gotta understand the basic properties of your evidence. And in chemistry, that investigation almost always starts with its weight, its mass. Okay, let's start here. You can think of atomic mass as the unique weight fingerprint for every single element. Seriously, just like your fingerprint is unique to you, the atomic mass of carbon, or oxygen, or hydrogen, it's unique to them. This is our first really solid piece of data. And what's cool is this idea scales up perfectly. I mean, our mystery powder isn't made of single lonely atoms, right? It's made of molecules. That's just groups of atoms bonded together. So to find a molecule's mass, you just add up the atomic masses of all its parts. Take water, H2O, that's 2 hydrogens, 1 oxygen. Add them up, and you get a molecular mass of about 18. Pretty simple, right? All right, so we know the weight of the individual pieces, the atoms, but that doesn't tell us the whole story. To really understand our sample, we need to know how many pieces are actually in that vial, and that is our next big clue. But here's the problem, and it's a big one. Atoms are just unbelievably small. You can't just peek under a microscope and count them one by one. There are trillions upon trillions of them, and even the tiniest little speck of powder. So, chemists needed a really, really brilliant workaround. And you know what? The solution is something you're probably already familiar with. Just like we buy eggs by the dozen, chemists count atoms by grouping them into the standard package called a mole. It's basically a chemist's dozen, just way, way bigger. It's a single unit that represents this impossibly huge number of particles. And this is that number, 6.022 times 10 to the 23rd power. It's called Avogadro's number, and yeah, it is a mind-bogglingly huge quantity of particles in just 1 mole. This is the crucial constant, the magic number that connects the tiny, invisible world of atoms to the world we live in, the world of things we can actually see and weigh. So what does this giant number do for us? Well, it connects directly to something we can actually measure in the lab, grams. That's what molar mass is. It's simply the weight, in grams, of 1 mole of a substance. And that is our breakthrough. We finally have a practical way to count the molecules in our powder, just by putting it on a scale. Okay, so now that we've got our counting method down, we can start to really interrogate our sample. By analyzing what it's made of, we can put together our first composite sketch of the suspect molecule. These days, modern lab analysis can give us a super precise elemental breakdown of our mystery powder. It literally tells us the percentage by weight of each element inside the compound. So for example, the machine might spit out a report saying our sample is, say, 40% carbon, about 6.7% hydrogen, and 53.3% oxygen. Now, this percentage data, this is the absolute key that unlocks the suspect's basic profile. Using those molar masses we just talked about, we can take these percentages and convert them into a ratio of atoms. It's the next logical step. And what that gives us is something called the empirical formula. Now, this is not the final ID, but it is a vital clue. It's like our first composite sketch from a crime scene. It tells us the simplest, most basic ratio of atoms. For instance, it might tell us we have 1 carbon for every 2 hydrogens and 1 oxygen. And hey, there's actually a clear 4-step recipe we can always follow to get this formula. It's super straightforward. Step 1, percent to mass. Just assume you have a 100-gram sample, so the percentages become grams. Step 2, mass to mole. Use the molar mass to convert those grams into moles for each element. Step 3, divide by smallest. Find the smallest mole value you calculated and divide all the other values by it. And finally, step 4, multiply to a whole. Sometimes you'll get a decimal, so you just multiply everything until you have nice, clean whole numbers. That's it. All right, we've got our initial sketch, we have our empirical formula, but now it's time for the final piece of the puzzle, the last piece of evidence we need to make a positive identification and finally close this case. So let's say our 4-step process gave us the ratio CH2O. You might be thinking, great, we're done. But hold on, this is a super common trap in a chemical investigation. Is that the true identity of our compound? Well, not necessarily. Remember, it's just a ratio. And here's why that's so important. The empirical formula, our sketch, just gives us the simplest ratio. CH2O tells us the relationship is 1 to 2 to 1. But the actual molecule could be a multiple of that. It could be C2H4O2, or maybe C3H6O3, or even something bigger like C6H12O6. These are all completely different compounds, but they all have that same basic ratio. So to find the true identity, the molecular formula, we need one last piece of evidence. And what is it? Remember that molar mass from earlier? We need to go back to the lab and measure the actual molar mass of our entire mystery compound. This is the final key. Okay, so now it all comes together. We compare the weight of our sketch, the empirical formula, to the actual weight of our suspect. The mass of our sketch, CH2O, is about 30 grams per mole. But let's say our lab analysis tells us the powder's actual molar mass is 180 grams per mole. See what's happening? 180 divided by 30 is 6. The real molecule is 6 times heavier than our simple ratio. So what do? We just multiply our simple ratio by 6, and boom, eureka! The true molecular formula is C6H12O6. We've totally unmasked our mystery powder. It's glucose, simple sugar. Case closed. So let's do a quick recap of our chemical detectives toolkit. We started with the fingerprints. That's the atomic and molecular mass. Then we used the mole as our universal counting tool. We gathered our initial evidence with percentage composition, drew up a composite sketch with the empirical formula, and finally, we made the final ID with the molecular formula. The real key takeaway here is that chemistry isn't just about memorizing stuff from a textbook. It's what the amazing scientist Michael Faraday said. It's an experimental science. It's about drawing conclusions from data. This whole logical process we just went through, that's the bedrock of discovery. It's how we design new medicines, create new materials. Mastering this kind of evidence-based thinking is an absolutely crucial skill for any serious student of science. And that leaves us with one last thought to chew on, identifying the molecule. Well, that's really just the beginning of the story, isn't it? The real question is, what does it do? How does it react with other things? In chemistry, the investigation never really ends.